Good evening everyone, my name is Avalpreet and today I'll be talking about basics of neural networks. So before moving into image classification problem, I'll briefly describe what linear classification is. So consider we have 3 points I1, I2 and I3. I1 as you can see is on the left side of this line represented by equation x1 plus x2 minus 6. I3 on the other hand is on right side and I2 is lying on this line itself. When we plug in these 3 points in this equation, we see that the points on the left side gives a negative value, the point over the line gives a 0 and the point on right side gives a positive value. So from this we can infer that if we are given a new point and we plug it into the equation, we can tell whether it lies on the right side or on the left side of that line. This is what forms the very foundation of image classification problem. What we do is, we first represent images as vectors or points in the n-dimensional space, and then we draw a hyperplane from which we come to know whether the point lies on the right side or on the left side of that hyperplane. Each side represents a different class of the problem. For example, if we have a cat and a not cat data and we want to classify that a given point is a cat or not, we will come to know that by plugging that value into the hyperplane. So first of all, we'll see how we can represent the images in form of vectors. So you can see that this image of a cat can be represented by a 3-dimensional matrix, each dimension representing a color channel, namely red, green and blue. Then this matrix is converted into a vector which is known as the image vector, and then this vector will be a point in the n-dimensional space which we will have to classify as our classification problem. So when we plot a training data of cat and not cat images, we find that all the cat images form a kind of cluster which are represented by red dots, and not cat images form a blue color cluster. Our objective is to find a hyperplane which can differentiate cats and not cats. So now we will more formally introduce this image classification problem. So let's say we have a set of vectors or images which is known as the training data, and it is labeled with y is equal to 0 means that image is a cat and y is equal to 1 means that it is not a cat. Now we want to classify a new set of data whether like it is a cat or not a cat. So for that we will have to draw a hyperplane in n-dimensional space where n is the dimension of each image. So a hyperplane's equation can be seen represented like a weighted linear combination of that image vector. The vector w and b are known as the parameters. Now objective of a machine learning problem or a neural network is to learn an optimal value of that parameter so that it can effectively do the classification problem for us. Now let us move a little deeper into this neural network problem. We'll introduce the structure of a neural network. So neural network consists of neurons or individual cells, which is basically a combination of two mathematical operations. First is the weighted linear combination, and then the second one is the nonlinear transformation. So let us say we have an image represented by a vector x. We first multiply it with w and add b, which is known as the linear combination. Then the output which we get out of that, we perform a non-linear transformation on that, that is we plug it into a function and then get a value out of that. This process is known as forward propagation. So the equation 1 is the linear combination and the second one is the non-linear transformation. Now for the purpose of computational complexity, what we can do is we can stack all the examples together in form of a vector or matrix and then perform these two operations simultaneously. Now let us talk a bit more about the nonlinear transformation. So the function which you see here represented by f is known as activation function, and you can use various types of activation functions like sigmoid or ReLU or tanh functions, and what they basically do is they take a value in a real space and then convert it into a value which is confined between two small values like 0 and 1 in case of sigmoid. Now once we have calculated the nonlinear transformation, let's say for example xi, we get the output ai. Now as I have already told that the value of this nonlinear transformation in case of sigmoid will be something between 0 and 1, and yi is the actual value of that labeled data, which may be exactly equal to either 0 or 1. So the objective of this kind of loss and cost function is to note that how close or far away is the predicted value from the actual value. When we do it for the entire dataset by taking the average of the loss generated by calculating on each dataset element, we get what is known as the cost function. So the objective of a machine learning problem is to minimize this cost function, which is inherently a function of w and b, which are the parameters of neural network. So as you know that to get the minimum loss, we need to differentiate this function with respect to the parameters. Since it is a function of two parameters, which is w and b, we do a partial differentiation here, and then we get what is known as the gradients. Now I'll introduce you to something known as the gradient descent. What gradient descent does is, it starts with a set of parameters, it calculates the gradients from the loss function, and then update the parameters so that the parameters get better and better and the loss function reduces. So this video explains what is going on. So we started with a random value of parameter, and after the gradient descent algorithm is run, we move towards a set of parameters for which the corresponding loss value is lower. And that is what the objective of our classification problem is. Now once we have obtained those optimal set of parameters, how does that reflect back in a hyperplane? So for that set of parameters, we have a hyperplane which can be seen or represented by this green line, which can effectively classify two sets of data, which is cat and not cat. On contrary, any random vector or set of parameters will give a hyperplane that doesn't effectively classify these two classes. Now I would like to briefly talk about nonlinear classification problems as well. Not all data is linearly separable, so we cannot solve the classification problems merely by using a single neuron. As in case of this, as you can see, you cannot draw a line to separate the red and blue dots. Instead, you need something like a circle or a set of hyperplanes. So what comes into picture after this is a multi-layer neural network. Each neuron introduces a hyperplane, and the combination of those hyperplanes forms a non-linear separating hyperplane, something like a circle. So the training of a multi-layer neural network is similar to that of a single neuron. It involves two steps. One is forward propagation, in which we calculate the output or the expected value of our labeled data, and then we calculate the loss, and finally with using the back propagation we update our parameter values. Now these are the fundamental equations which are used to update the value of each parameter. In forward propagation, in each layer represented by L, we first calculate the weighted linear combination, and then we do the nonlinear transformation. In back propagation, for each set of parameters corresponding to each neuron in each layer, we need to update that weights. This is done using these following equations. This is the summary of multi-layer neural network model. We first initialize all the parameters, then we perform a forward propagation, calculate loss, calculate the backward propagation, update the parameters, and then repeat this process until the value of loss function stops changing. This is a trained neural network now, and which can be used to predict the testing data. Thank you. Alright, now we'll try to code this image classification problem. So what we have with us is a data set in which we have some cat images and then some other images which are not cats. We'll try to train a single neural network and try to classify these two categories of problem. That is, our neural network should predict if the image that we are feeding him is a cat or not a cat. For that, let us first install some basic libraries. Then we load our dataset. I'll try to show you the various pictures that are there in this dataset. For example, this is a cat over here. You can see like this is a house. This is a bird. So if we see the shape of our dataset, what we see is that there are 209 images and each image is of the dimension 64, 64 and 3. If you remember our image PPT, what I told was that there will be 3 channels for each image and then it will be a matrix. So it is a 64 cross 64 cross 3 matrix which represents our image dataset. Next, what we did was we converted that each image into a vector known as image vector, which is formally known as flattening of the data. Now, if we see the shape of our flattened data, we see that there are 209 columns in our dataset and each column is of the dimension 12288, which is 64 times 64 times 3. So basically each column represents the image vector of each image, and there are 209 such images in our training data. Now value of each element in this vector is basically the pixel intensity value. That value can be anything between 0 to 255. So we need to normalize this data by dividing it by 255 so that all the input values are between 0 and 1. And this can be done by this code. Finally, let us start with our functions that we'll be using. As you know, the activation function that we'll be using is a sigmoid function. So we have defined that sigmoid function. Next, we have made this function known as initialize with zeros. What this does is it initializes our parameters, which is w and b, with zeros. Alright, so next is our propagation function. As you know that in a neural network there are two main operations. First is the forward propagation, then it is the backward propagation after the loss is calculated. So in our propagate function over here, we feed it with the input data and the labels and initialized parameters, which are initialized with 0 in this case. We first perform the forward propagation by computing the activation. As you can see that this has been done in a vectorized format, which means we have calculated the activation for all the examples simultaneously. Next, we calculate the cost for all these input vectors by comparing the predicted output and the actual output. We perform the backward propagation to update our parameters, and finally we store all these updated gradients in a dictionary known as grads. Alright, so optimize function, what it does is this repeats this forward and backward propagation in a loop until the value of loss function reduces and then stops reducing further. So as you can see that we have used a for loop which takes in the number of iterations, that is the number of times we want this forward and backward propagation thing to run. We call the propagate function each time in this loop, calculate the cost, update, get the grad values, that is the gradients. Then what we do is we use this gradient descent formulas to update the parameters. Finally, we store the parameters as well as the grad values in the form of dictionaries. Alright, next is the predict function. Now, from the trained neural network, when we feed it with the testing data, we need to predict whether it is a cat or not a cat. So this function precisely does that. So what it does is, first it calculates the forward propagation for the input image, and then since it is a sigmoid function, so the output value has to vary between 0 and 1. If the value is more than 0.5, it is considered to be a cat. If it is smaller than 0.5, it is considered as not a cat. Finally, we summarize all these functions in form of a model, which is our basic linear classification model, and then we run this function. So next, now we will see by feeding it with the number of iterations and learning rate, as well as whether we need to print the cost or not. We give it the training dataset as well as the test dataset, and we try to see the accuracy of our model. So as you can see, with each iteration, like we had fed it with the 2000 iteration input value, so you can see the cost value is reducing as the number of iterations are increasing. This means that our neural network is doing a good job and our parameters are moving towards the optimal parameter. On training data, you can see that we have achieved 99% accuracy. What that means is, for over the training data with the given set of optimal parameters, if we feed an image from the training data set, there is a 99% chance that it can predict whether it is a cat or not a cat. However, on the testing data set, we have a very low accuracy of 70. Now, there are several ways of improving this test accuracy, which can be by increasing the number of layers, increasing the number of iterations, using different type of activation functions, and that is more of like a trial method. So that is known as hyperparameter tuning. Now we will try to test our neural network with real world data. So let us take an image out of Google and try to predict whether it is a cat or not. So I had stored that image in our directory, and then when we pull in that image and then run it over our algorithm, so this is the image and our algorithm is predicting it to be a cat, which is doing a pretty good job. So you can try it with different kind of images and see how good this neural network is. Thank you.